Hello and welcome to this video on how to interpret factor loadings in CFA and SEM. My name is Geiser. I'm an instructor and statistical consultant with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistics such as structural equation models, factor models, multi-level models, latent class models, and latent profile models. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional resources, including a link to my free weekly statistics newsletter, as well as courses that I teach for QuantFish. In this video, I want to talk about the interpretation of factor loadings in structural equation modeling and confirmatory factor analysis. Many people who are new to the structural equation modeling framework or the confirmatory factor analysis framework, but who are used to doing exploratory factor analysis, are confused about the interpretation of factor loadings in SEM and CFA, because in SEM and CFA, unlike exploratory factor analysis, we first of all deal with unstandardized loadings, whereas in factor analysis we typically only have standardized loadings. And so that already is something that confuses people sometimes, that there are two sets of parameter estimates, two sets of factor loadings, unstandardized factor loadings and standardized factor loadings. And so here in this video, I want to shed light on both unstandardized factor loadings, what do they mean, and standardized factor loadings, how are they interpreted, what is the difference. And I have as an example here a very simple confirmatory factor analysis model with two factors. Each factor has two indicators, and I want to go through the interpretation of the factor loadings in this simple model. This model was estimated in the Mplus software, but you could estimate a similar model in many other programs as well, and you would get the same or very similar output. For example, you could use the lavaan package in R, or you could use AMIS, or you could use Literal or EQS or OpenMX or something like that. So pretty much the same thing. And Mplus also generates this path diagram for you when you run a model, and so you can look at the estimates in the path diagram. The numbers that are shown are the point estimates of the parameters, and then in parentheses you have standard errors that are also estimated, in this case using maximum likelihood estimation, which is a default estimation method for continuous outcome variables in CFA and SEM. So let's take a look at the factor loadings. And so first of all, what you see here are unstandardized parameter estimates, which means that in this model, or in this version of the model estimation, none of the variables have been standardized. Neither the y variables, the indicators of the factors, nor the latent variables f1 and f2. So they are all unstandardized. Notice furthermore that each variable in this CFA model loads only onto one factor. y1 and y2 only load on f1, whereas y3 and y4 only load on f2. And the two factors are correlated, or in the terminology of exploratory factor analysis, we would say they are oblique. They are not orthogonal. They are allowed to correlate. You can see there's a covariance estimate here between them, 0.39. So since the factors have not been standardized, this is interpreted as a covariance, and so it's somewhat difficult to say whether this is a strong linear association or a weak linear association, because you have to take into account the variances, which are also provided here as 0.77 and 0.51. Later in the standardized solution, we will see that this turns into a correlation estimate, and then this is easier to interpret. On the right hand side, you have the error variance estimates with their standard errors for the observed variables. That's also something that is unfamiliar to many people who start out with exploratory factor analysis, because there is typically no such thing that we look at when we use EFA in SPSS, for example. Then you don't get error variance estimates. Now, further note that when we look at the loadings, you can see that the first loading here is actually exactly 1.0 with a standard error of exactly 0. And the same is true for the first indicator of F2, which also has a factor loading that is exactly 1.0. Now you could ask yourself, what is that about? This doesn't look like it's an estimate. It looks like this is a fixed parameter. And in fact, that is the case. So when we look at the unstandardized solution, the default in many software programs, including Mplus, is that the first factor loading is fixed to 1 in the unstandardized solution. And that is for identification. So otherwise, we could not identify the metric or the units of measurement of the latent variables because they are arbitrary, or we could say not uniquely defined. So it basically doesn't make sense, or excuse me, it basically doesn't make a difference whether you measure F1 in units from 0 to 10 or from 10 to 1000. It's completely flexible and arbitrary what metric F1 and F2 are measured in, what the units of measurement are. And so in order to constrain, in order to set the metric of these factors, we bind them, so to say, to one of the observed variable metrics. So the fixing of that factor loading is done so that the metric of F1 can be identified, and here also for F2 we are fixing the loading so that the metric of F2 also can be identified. An alternative way would be to fix the variances, meaning standardizing the factors to a variance of 1, and then the loadings could all be estimated. And that shows you already kind of that the loadings are kind of arbitrary in a way, at least in the unstandardized solution, because it really depends on how you set the scale of the latent variables. And you could alternatively, for example, fix the loading of the second indicator and estimate the loading of the first indicator, and that wouldn't make a difference for the overall model fit. It also wouldn't make a difference for other parameters later on that we will see in the standardized solution. So the unstandardized loadings are kind of arbitrary in a way because there's no unique definition of the factor metric, and so that has to come from somewhere, and it can either come from fixing one of the loadings to 1 or from directly fixing the factor variance to a value, for example, to 1. And so this is one reason why the unstandardized loadings often are not of such great interest, because they are subject to these, in many cases, arbitrary constraints to set the factor metric and to identify the model, but nonetheless they have an interpretation. And so what is the interpretation? The interpretation means, so say when you have the variable y1 is part of a regression equation where y1 is equal to an intercept plus the factor loading times the factor plus the error variable epsilon. And so the factor loading then is a multiplicative parameter, a regression slope parameter in a linear regression of this variable on the factor. So it means that for every 1 unit change in the factor, we expect a 1 unit change in the indicator. So it has exactly the same interpretation as a linear regression coefficient in bivariate linear regression, because here the variable loads only onto one factor. So it's a linear regression equation. y1 is equal to intercept plus slope factor loading times factor plus error. And so the factor loading then is a linear regression slope parameter, and that's exactly how it is interpreted. And so then this is the one that is fixed anyway, so there's no deeper interpretation here other than that this is the one that is used to identify the factor metric. What is interesting here is that the second loading, which is freely estimated and is estimated to be 0.978, is very close to 1. And so that tells you something. So it's all relative, so to say. It tells you that the second indicator has pretty much the same metric as the first one, because this is barely different from 1. And probably if we constrained this loading to 1, the model fit wouldn't get any worse, or not much worse, meaning this is probably not significantly different from 1. And so that would be an interesting piece of information, because it could mean that those two indicators, y1 and y2, are essentially tau equivalent, as we say in classical test theory. So meaning they are essentially measuring the same true score variable except for potential differences in their means. But there's no difference in the units of measurement here, because this factor loading is estimated to be so close to 1. And so for the second indicator, then also a 1 unit change in the factor would be expected to be associated with very close to a 1 unit change in the indicator as well. And when you look at y3 and y4, you can see that also the factor loading for y4 is estimated to be close to 1. It's a little higher than 1. It could be tested whether this factor loading is statistically different from 1. And then if it weren't, that would also mean that these indicators are essentially tau equivalent, that they measure the latent factor in the same with the same units of measurement. So that could be important information. Other than that, those loadings really express differences in the scaling of the indicator. So they really, so to say, help us to express when we have scales that are measured in different units. For example, if you measured a latent factor temperature and one scale was in Fahrenheit units and the other scale was in Celsius units, then the factor loadings would be estimated such that you have exactly the conversion between Fahrenheit and Celsius. And so you could even fix the loadings then, because that conversion is known. We know that we can make that calculation from Celsius to Fahrenheit, where Fahrenheit is equal to 32 plus 1.8 times Celsius, and so you can easily then calculate Fahrenheit degrees from Celsius degrees, and the multiplicative parameter here is 1.8. That would be the factor loading. So really the factor loadings are scaling parameters in the unstandardized solution that allow us to take into account that different indicators of the factors may actually not be tau equivalent or essentially tau equivalent, but that they may only be congeneric, as we say, where they could have different loadings. Now, what is typically more looked at in a solution is the standardized factor loadings, and you can view these as well in the Mplus output when you click on View STDYX estimates. Those are the estimates from the completely standardized solution where both the observed and the latent variables are standardized to a variance of 1. And so then, yet now you can see that here the values for the variances of the factors are 1.0 with no standard error, because now these are fixed parameters. So the variances of the latent variables are fixed, and so are the variances of the observed variables. And as a result, we can now estimate all factor loadings, because now the identification of the factor metrics comes from the standardization. So we no longer have to fix a factor loading, but instead all the factor loadings can be freely estimated with their standard errors here shown in parentheses. Also, now this value here for the double-headed arrow indicates a correlation, 0.62. This can now be interpreted as a correlation because the variances are 1.0, so that's then a standardized covariance, and a standardized covariance is equal to the Pearson product moment correlation. So the latent correlation between the factors here is very substantial, 0.62. Now these loadings here have a different interpretation than the unstandardized loadings, since now all variables have unit variances, and so because each variable has a loading on only one factor, those standardized factor loadings can be interpreted as correlations between the variable and the factor. For example, the correlation between y1 and f1 would be 0.893 according to these estimates. So there's a very strong association, very strong linear correlation between f1 and y1, indicating that y1 is a fairly reliable indicator of f1. This standardized loading squared gives you an R squared value, which is also output by software programs for SEM such as Mplus. And then this squared correlation value, meaning 0.893 squared, gives you the reliability of the indicator. So the squared standardized loading in a model like this is an index of reliability, and I'll show you that later on in the Mplus output with where all the numbers are printed. The R squared is not included here in this path diagram. But so that's the interpretation then. You can interpret these standardized loadings as correlations between each variable and the factor, and they tell you something about how reliable each indicator is. The closer the loading to 1, the more reliable the indicator. The smaller the standardized loading, the more unreliable this indicator as a measure of the factor, or the less valid. Yeah, so this could indicate a lack of validity and or a lack of reliability of the indicator as a measure of the factor in question here. And so that's why we typically aim or desire to see loadings that are close to 1, above 0.8 maybe, above 0.9 would be even more fantastic. So the closer to 1, the better, because then that indicates that the variable is strongly correlated with the factor, that it's a good indicator of the factor, and that is what we want. We want good measures of our latent variables. So standardized loadings are correlations between variable and factor in most cases, though not in all cases. So this is the case here because each variable has a loading only onto one factor. When you have a model where you have cross loadings, meaning where variables load onto more than one factor and the factors are correlated, then you can no longer interpret the standardized factor loadings as correlations for those variables that have double loadings. That's very important. So for example, when you have a latent growth curve model where indicators load, or some of the indicators load onto both an intercept factor and a slope factor, an intercept and slope factor are typically allowed to correlate, then many of the standardized loadings will not be interpretable as correlations anymore for those variables that have double loadings. And so then those would be partial standardized regression coefficients that have the same interpretation as a partial standardized regression coefficient in multiple regression with correlated predictor variables. And so then they are no longer correlations. They could even be larger than 1. This is sometimes something that we see in growth curve models when we have for example, a negative correlation between intercept and slope factor, then sometimes the loadings of some of the indicators will go above 1 in the standardized solution, and that's not necessarily a problem because those are not correlations, they are partial standardized regression coefficients. Likewise, when you have factor models where you have cross loadings because indicators measure more than one factor and the factors are correlated, then you have to be careful. You can no longer interpret those standardized factor loadings as correlations. So that's strictly only applicable when you have a simple structure like here. And this is something that parallels actually what happens in exploratory factor analysis when you have an oblique solution, meaning when you do oblique rotation of your factors in exploratory factor analysis so that the factors after rotation are correlated, then we know that there's both a pattern and a structure matrix, because then the factor loadings can no longer be interpreted as correlations. Instead, they are partial standardized regression coefficients. And so then we look at both a pattern matrix and a structure matrix, meaning both loadings and correlations. So that's the same issue in CFA. However, typically in CFA, we have a strict simple structure like here, and then that problem does not occur. Now let's take a look at the Mplus output for this model here as well, so that you can see where we have the R squared values. And so when we go to our standardized solution STDYX, you can see the loadings again that we just looked at in our path diagram. Here's the factor correlation of 0.62. We have intercepts, we have the standardized factor variances, and we have the standardized residual variances. And then below that in Mplus, we get our R-squared values. The R-squared values are the squared standardized factor loadings. So those indicate the loadings here squared. So for example, the first loading is 0.893, so 0.893 squared yields 0.797, so that's the squared standardized loading, or R square, which can be interpreted as a measure of reliability, and it would indicate that 79.7% of the measured variance, so the variance in the indicator y1, is true score variance or is factor variance, and so that means basically 80% of the observed variance is reliable variance, only about 20% is unreliable or error variance, and the unreliable or error variance is provided by the standardized residual variances in Mplus. So this would be the portion that is missing. 0.203 is the error variance component, 20.3%, and so this number plus this number yields exactly 1.0 or 100% explained variance. So that's to say how the standardized factor loadings are linked to R squared or reliability, and that's a very useful piece of information when you run a factor model or a structural equation model. Then you want to know what proportion of the variance in each indicator is reliable variance versus error variance. I hope you liked this video and learned more about how to interpret factor loadings in CFA and SEM. If you did, please hit the like button, subscribe to this channel. Don't forget to check out the description for additional resources, and I'll see you next time.